We go like crazy in here. Okay, so we're in the unit of exponential and logarithmic functions, which is one of I really like this unit. Okay, so exponentials. I'm not talking because I have to think. So exponentials have the form y is equal to a times b raised to the x, where a is what we call our initial value and b is the growth or decay factor. It's going to be exponential growth if your b value is greater than 1, and it's going to be exponential decay, it's getting exponentially smaller, if that b value, the factor is less than 1. So like 0.2 is less than 1, or 1/2 is less than 1. That's decay. So b cannot equal 1, and the reason that is because if b was 1 raised to any power, 1 raised to the first, second, third, fourth, fifth is always 1, so it's not exponential. So b can't be 1. It's just not considered exponential. So these are just some examples of some exponential growth and decay. So this would be a starting value of 3, correct? Everybody? Starting value of 3, initial value, and then our factor is 2, so it's a growth factor. Now think about that, does make sense, right? 3 times 2 to the first power, it's getting larger by a growth, like multiplying by 2, right? You plug in 2, that's 2 squared, so it's happening twice. Does that make sense, everybody? Okay, so this would be growth. This would be an example of exponential growth, starting with $20, 1.10. It's growth. That means 110% worth, correct? It's worth 100% plus 10% more of $20. Okay, so this would be exponential growth. This one is exponential growth. Our initial value is -2, and then we are getting exponentially smaller, but it's growing smaller. Okay, so this one is exponential decay, because 0.20 is less than 1. Our initial value is 4. So we have seen exponentials in the past, and we should know kind of basically how these work.
Hey, what does this say in the box?
So like b cannot be 1. That's what I was just saying. Why can't it be 1? It's not exponential. Because if b is 1, that's 2 times 1 to the x power. That's not exponential. Because no matter what, it's going to be 2. So that's what I was saying with that. Okay, so everybody, exponential graphs. First of all, we should be able to graph anything because we're just plotting points. So let's look at y is equal to 2 to the x. You don't even have to take notes, just look what's happening here. So first of all, let's list out some x, y points. So let's plug in some negative numbers, maybe like -2, for example. So wouldn't that be 2 raised to the -2 power? Maybe we should even go bigger. Yeah, let's go like -4. So that's 2 raised to the -4 power. Isn't that 1 over 2 to the 4th? Which is 1 over, what's 2 to the 4th power? Go, go, go. We're all participating. What is it? Right, 2 times 2 times 2 times 2. 4 times, right? -4. No, this one's growth. Isn't this, so our initial value is 1. Our factor is 2. Isn't 2 greater than 1? So it's exponential growth. I'm just plugging in points here to see what the graph looks like. Yes? So -3 is 1 over 8, correct? -2 is 1/4. -1 is 1/2. Let's plug in 0. We get, what's any base to the 0 power? 1. Any base to the 0 power is 1. So let's plug in 1. We get, no, plug in 1, guys. And we plug in 2, we get 4. Okay, let's plot these points. So we're going to -4, barely up at all, correct? -3 up a little more, -2 up a little bit more, right? -1 we're up to a positive 1/2, right? Everybody, to see what's happening here. Over 0 up 1, over 1 up 2, over 2 up 4. So do you see how it's just getting smaller and smaller but never crossing 0? As this is going larger and larger, or smaller and smaller, depending on how you look at it, you get what I'm saying? This is getting closer and closer to 0, isn't it? Okay, awesome. Look, isn't it just going to get closer and closer to 0? It won't ever touch, no. So this is exponential growth. So our x-axis is an asymptote, true. Asymptote. Okay, so a couple things, guys. Notice, the initial value is 1. Do you see how we started at 1? So that will be true always. It'll cross the y-axis, unless there's a shift left or right, that is.
Yeah, but if it's
unless there's a shift. We could shift this now, right? Okay, gotcha. Yes. Good. Yeah, it's always going to cross. But do you see what I was saying with non-shifted? Do you notice how it crossed there? Because that obviously makes sense. 2 to the 0 is 1, so it's going to cross at the initial value, the y-axis, right, everybody? Okay, if we go this slow, we're not going to get through the lesson. Okay, here we go. So let's also graph 4 to the x. So everybody, let's plug in -4. What do we get? 4 over 1 over 4 to the 4th, which is what? 1 over, guys, can we all please? 256. That's a really small decimal, right? Let's go with -2. That's 1 over 16. Let's go with -1. That's 1/4. Let's go with 0. What's any base with 0 power? Okay, let's plug in 1. We get 4. Let's plug in 2. We get 16. So if I graph this one, I'll graph it in P. We're starting at 1, correct? And it's growth over 1 up 4. And then it would be over 2 up, clear up to 16. You see how it's getting really exponentially larger by a factor of 4. Then it's getting smaller. Look, so at -1, we're down a 4th. So you see how it's just getting smaller quicker? Okay, perfect. So, very good. That's just graphing 2 on the same thing. Okay, awesome. So we understand how to graph those. So let's look at this one. Can anyone tell me what that shift is? We just graphed 2 to the x. Almost, you were almost there. This is a reflection over the y-axis. In front of x is when it's a reflection over the y-axis. So you were close. So let's just plug in some values. Let's plug in -4. That's 2, -4. Won't that be positive? 2 raised to the negative of a negative. So what's that going to be? 2 to the 4th, right? It is, we said, 16. Right? Okay.
-116. But, yeah.
Plug in -2. 2 negative of -2. Won't that be 2 squared? Which is 4. -1. That'll be 2. Correct, everybody. 0, we get 1. Let's plug in 1. That's 1/2. Plug in 2, 1/4. Okay, so we're going this way now. We're going -4 up 16, clear up there. -2 up 4 over -1 up 2 over 0 up 1, and then it's getting smaller. So it looks the same. It's just a reflection over the y-axis. Everybody seeing what's going on there? Okay, we're not going to graph this one. Okay, cool. So here we go. Let's graph this one. So we could just make a table of values, and we can just think about it. There's our initial value. If x equals 0, 3 to the 0 is 1. So where are we going to start? 2, right, everybody? Let's plug in 1. 6. Let's plug in -1. A decimal, right? 2/3, right, guys? Okay, let's plug in -2. So isn't it just going to get smaller and smaller? That's what we're recognizing here. Okay, so this was exponential growth, right? 3 is greater than 1, so it's growth. What's the domain of this?
-infinity.
Good, all real numbers. What's the range? 0 to infinity. Does it include 0? No, 0 to infinity, because we have an asymptote at 0 here. It is not going to cross. It's going to get smaller and smaller. Okay, what's our y-intercept?
0, 2.
Good. Over 0 up 2. That's our initial value, notice, right? And then as x is approaching positive infinity, what's our function approaching? Positive infinity. As x is approaching negative infinity, what's our function approaching?
0.
0. You guys are going to be so good at limits when you go on a calculus. Half the limit. Yes. No, we were just plugging in points. So we plug in 0, we get 2. Plug in 1, 3 times 3 to the, you know what I mean? Like we're just plugging in values. Okay, let's do this one. So isn't this going to be a reflection over the x-axis? Okay, so let's plug in 0, we get -2, correct? Let's plug in 1. That'll be -6. Let's plug in -1. That's going to be positive. Wait, what is it going to be? Negative 2/3, you're right.
Going over that.
You just flip it, right? Do I need to show the work for that? So it's just going to keep getting closer and closer, but it's still not going to cross. Okay, so we have still our asymptote at 0, or y equals 0. Here we go. What's the domain? All real numbers. What's the range? Negative infinity up to 0, not including 0. Our y-intercept is negative 2. As x is approaching positive infinity, f of x is approaching negative infinity, right?
Yep.
And as x is approaching negative infinity, our function's approaching 0. We don't have time to do that. Okay, so now if we transform this, so now we're taking and moving them. So shifting for all functions works the same. So this is still our initial value. This is still our factor, growth or decay. Now we know shifts left and right are always grouped in with x. Our shifts up and down, our sign stays the same, and that's added to the outside of the function. The negative is a reflection over the x-axis. So if I said to you, describe in words the shift from the parent function. My parent function for this, guys, is y is equal to 2 to the x. Yeah? Then we would say right 3 up 1, correct? Okay. So then this one, our parent function would be y is equal to 2 raised to the x still. It's a stretch of 3, reflection over the x-axis, left 1, down 4. So does everybody see how that's working? Okay. So we should know, like, transformation for all functions is the same, so it's not any different than anything else. So if I said to you, graph this exponential, the first thing I'd say is, what are my shifts? Right 1.
Up 2.
Up 2. Okay, so that's our new origin, right? Right 1 up 2. There's our new origin. So won't my new asymptote be here if it used to be at 0?
Yes.
It will be. Okay, very good. So then from here, we're going to go up, and you can just plot points. If you plug in 1, you get 1 minus 1, which is 0. 3 to the 0 is 1. 1 plus 2 is 3, right? And then if we plug in 2, that's 3 plus 2, which is, and so on. So what's going to happen is, and then let's plug in 0. So that's 3 raised to the negative 1, right? 1/3 plus 2. So that's 2 and a third, right? So going over here to 0 and going up 2 1/3. So that's barely any, right? So it's just going to get smaller and smaller and never cross the asymptote. It's exponential growth, right? There's our factor, which is 3, which is greater than 1. So what's my initial value?
3.
1. Right? 1? Okay. So then our domain for this is all real numbers. Our range is 2 to infinity, not including 2. And our y-intercept is that, right? It's when x equals 0. Good. We need to do parentheses. Good catch. So what's our y-intercept? Isn't it that value? Which we said was 2 1/3.
Yeah.
Okay. So what is that as a mixed fraction? Yeah, 7/3, right? Let's add one over the same denominator. Okay, as x is approaching positive infinity, our function's approaching positive infinity. As x is approaching negative infinity, what's our function approaching? You guys are so smart. It's approaching 2. Okay, good. Thanks. So I was going to let you do some homework, but we just don't have time. So we've got to keep going, okay? All right, so now we're going to talk about, it's called the natural base e. This is just a special exponential. So a lot of people see this e and they think it's a variable, but it's not. E is a number. It's approximately 2.7. So when we see y is equal to e to the x, that's just no different really than y is equal to 2 raised to the x. It's the exact same thing. It's just e is 2.7. So e, we could think of it as this more so. Y is equal to 2.7 raised to the x. They're the same thing. But we're going to use e in our calculator. So everybody go to your calculator. Let's make some values here. E is, yeah, very similar to pi. It's just a number. So let's plug in -1 into our calculator. You got to use the e button. So pull up your calculators.
I see it.
It's second ln. Second ln. That's the one you should be using. So e raised to the -1. So you'll do second e. Type in -1, close your parenthesis, hit enter. What's the decimal? 0.3. Okay, let's plug in 0. We don't even need a calculator. What do we get? 1. Plug in 1. What's anything to the 1 power just itself? So it won't be approximately 2.7. Okay, let's plug in 2. So type in e raised to the 2 power. So we could graph this negative 1 up 0.3 over 0 up 1, which makes sense. Our initial value is still 1 over 1 up 2.7 over 2 up 7.4. So it's an e looks just like all of our other exponentials. It's just a special. Okay, so asymptote's still here at 0. Okay, so if I said to you, given f of x is equal to e to the x, given our function e to the x, if I said find f of 2, you just plug in 2, right? It's very obvious. Plug in f is negative 2. But what I would want to see from you, so this would be f of 2 is e to the 2nd power. That's a pretty answer, so then you could give me the decimal answer as well. So e to the negative 2 looks like this. The pretty answer should be 1 over e squared, right?
So that's e squared.
1 over e squared. That answer is more pretty. I would like to see that answer and then also the decimal.
We'll understand that.
Yep.
And I
Yeah, that's fine. But I want to see this. 2. Okay. Cool. Okay, so given a car is worth $20,000 and its worth is depreciating at a rate of 20% per year, how much will the car be worth in 5 years? So isn't our initial amount it's worth is $20,000? And then our factor is it's depreciating at 20%. So 0.8. It's worth 80% of its value, correct? And then a lot of people want to mess up and put 20. Okay, then how much will the car be worth in 5 years? $6,553.6. Yeah, that's how much it's worth. No, that's how much it's worth. So that's not very much money. You're losing a lot of money on that part. He says the bank is offering an annual interest rate of 2% on a savings account. You want to save for your child's college, so you put $500 in an account and make no future deposits or withdrawals. How much money will you have in 20 years? So this is a basic one.
1.02.
500 times 1.02 raised to the 20. And that's not very much money. Guess how much that comes out to be? $742.97. Looks like your kid's not going to college. Yes. Says, good question. It's worth 100% of its money, right? They're getting 100% of their money. 2% is 0.02. Yeah, it's interest. Okay. That's where we do those. Hey, this is a keyword. This is new. Maybe new. So this is compounding continuous. So we just did basic ones. Now, here's the keyword. If you're getting interest compounded continuously, that means you're getting interest at any given second, at any given time of the day. You're always getting interest here. So this is one of the most familiar examples of exponential growth, is the investment earning of continuous compounded interest, and it's PERT. So A is equal to P times E raised to the RT. So P is the principal or put down amount, that's our initial value. E is the growth factor, which we know E is 2.7, so that's 270% worth, right? 2.7? 270%, okay? And then the time in the account is T and R is our interest rate. You have to put it in decimal form. So we're calculating numbers. If I said 3%, you'd have to put it in 0.03. So PERT. Now that is anytime you see the keyword, and only when you see the keyword compounding continuously is when you use PERT. We only ever use this formula, PERT, when you see the word compound continuously. So if I say to you, I give you this amount and it's compounding continuously, that's when you know I'm using the PERT. Yes. Okay, so then, do you have that formula written down? Okay, next formula. This is compounding interest per year. So compounding interest per year, this is the formula you'd use. A is equal to P times 1 plus R over N raised to the NT. So this is getting, you know how a minute ago we were just doing some examples? That was only considering that we got interest once per year. Now we're dealing with maybe you're going to get interest more than one time a year. This is the formula we'd use. So P is still the principal or put down amount, and then 1 plus R over N. So R is the rate of interest, N is the number of times you get interest in a year, the number of times you get interest in a year. So if you get interest twice in a year, you put a 2 in for that. And then T is the time in the account. So we use compound interest if you see the word compounding continuously, and you use this formula if you see just you're getting interest this many times a year. So those really easy examples, what we're technically doing is putting a 1 in here and here, because then you're only getting interest once a year. Yeah, it was down. So it says a total of $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if it is compounded quarterly, monthly, and continuously. So here we go. If it's getting interest quarterly, then, so like that's the thing is in the real world, guys, when you go into the real world and you guys start like taking out mortgages and stuff, different banks will offer different things and you will have to take into consideration many things. So if something offers this really good interest rate, but they only give it to you once a year, then it might not be as good as a lower interest rate getting compounded many times a year. Does that make sense? Getting interest more than just once. You have to take into consideration those things and do the math when you get into the real world. Okay, so here we go. There's our formulas over there. So quarterly, we're getting it how many times per year?
4.
4. So we're getting it 4 times a year. So let's use our formula. So here we go. We're starting with $12,000 and then times 1 plus our interest rate is 9%. So 0.09 over N, which is the number of times. Nope. Here's our formula. And then, oh yeah, good question. So this isn't 1.09. The reason we were doing that a while ago is because we knew that we were getting interest only once a year. So what we were doing is putting a 1 here. So then right here, won't that become 1.09?
Oh,
Does that make sense? Okay, and then raised to the N, right, guys? 4 times 5 years. T is time. So you type it into your calculator. I do want you to make sure you can type it in right. So everybody type it in and then make sure you get this.
Whoa.
So their money went from $12,000 and 5 years later they walk out with $18,726.11. Okay, monthly, that means you're getting it 12 times in a year. So then we would do 12,000 times 1 plus 0.09 is still our interest rate, but now we're getting interest 12 times. So 12 times 5. So make sure all of your this is like in your your calculator. That's got to have parentheses around it when you type it in. So this one's coming out with $18,788.17. So a little bit more than this one, but not a whole heck of a lot more.
Continuously only once a year?
No, continuously is like you're always getting interest at any given time. But you'll be surprised at how much it's not that big of a difference. So here we go. That's not a very big difference, right? It's kind of interesting. And we could get into this of why that is. We could get into why that is, and we can talk about it next time. Maybe we just don't have time right now to talk about it. But there is a reason, like as we grow to infinity, it eventually starts to kind of cap out.
Like hardly any difference.
Yeah, there's not a huge difference, which is interesting, right? Because this was 4 times a year, this was 12. Does that make sense? And it's not a huge difference. We could talk about why later. We just don't have time now. So we have 12,000 times 1. Actually, we should be using PERT, correct? Yes. Continuously. So put down amount is 12,000. Then our factor should be E. Sorry, that should just be E right next to it. Our rate is 0.09 and then T is 5. So type it into your calculator. And we get $18,819.74. So not a whole lot more than that. You know what I mean? It's kind of interesting. Like you're always getting interest at any given time. Yep, always getting interest. So we could get, well, E is the number 2.7, right? That's our factor. Like that's just the rate, like that's That's when they're getting interest at that rate. We could get into it, and we absolutely could if we just had more time. So I'll make sure that we talk a little bit about that next time, but we just don't have time today. Does that make sense? Our book does get into it. They give a whole proof of where E comes from, and I was going to go through it, and then I deleted it because I'm like, we're not going to have time if we do test prep. Yeah. Yeah, exactly. A lot of times people will think that, if they say that you're getting compounding continuously, people will think, oh, wow, that's crazy. I'm going to go with that one. And then over the long haul, it's really not a big difference here. So like maybe you put down more money, but it's, you know what I mean? I don't know. I couldn't think of a very good example off, but this does trick a lot of people. Because really it wasn't that much better than this. You know what I mean? Yeah. Okay, cool. So, next thing is the one-to-one property. So one-to-one means every element in the range, which is output, will correspond to every exactly one element in the domain. So I'll say that again. One-to-one means every element in the range, which means the output, so 9, for example, will correspond to exactly one element in the domain of the function. So if I said to you solve for x, what would you say? 2. X equals 2, right, everybody? So how did we get that? We said 3 to the x is equal to, base 9 is the same, 9 is the same thing as 3 squared, isn't it? So now since they're the same base, can't we just say x equals 3? X equals 2. Because 9 is the same thing as 3 squared, correct, everybody? You guys see what I did there? Yeah. Changed it to the same base, so x equals 2. Because 3 squared is 9. Does everybody see what I did? No?
Well, I see what you did.
9 corresponds to this square, correct?
How do you know that? Is it given?
Yeah, so if we're told given the one-to-one property, then we know there's only one answer for this. That means that this has exactly one answer. Like this x can only be one solution. Nope. We square root that. Well, like that. But how did you know that? Why would we just square root of that would be 3. So that didn't help us, right? You're right. So we will learn how to algebraically solve this later, but not right now. A different way. Okay, let's solve 46 in the book. So if I said to you solve for x, we don't want to have to just do trial and error. I want to see some work. So this is 2 raised to the x minus 3. Let's write 16 as base 2. So 2 to the what power equals 16? 4. So we have this. Since we have base 2, we can now just set those equal and solve. So x minus 3 equals 4. Solve for x. X equals 7, right? Yeah. So now look, let's even check it. 2 raised to the 7 minus 3 equals 16. That's 2 to the 4th equals 16. Isn't that true? Yeah. So I can check all my answers here. So you're just doing it and rewriting it in the same base, and then you can just use the exponents to solve.
That's actually very cool.
Yeah, it is cool. So this 48 is a little bit harder. So this is 125, and this is base 1/5. 5 to the what power equals 125? 5 to the 3rd power, right, everybody? Well, this is 1 over 5, but isn't 1 over 5 flipped over a fraction? So couldn't we rewrite this as 5 to the negative 1 raised to the x plus 1? Isn't this the same thing as this, guys? So now look, they're both base 5. So I'm going to scoot it down here. So we have this. 5 raised to the negative 1 in parentheses, and then x plus 1 equals 5 to the 3rd. So raise a power to a power and you multiply. So we should be distributing that negative 1 through. So we're rewriting it. So we have 5 raised to the negative x minus 1 equals 5 to the 3rd. Now they're both base 5, so now we can simply use algebra using the exponents to solve. Negative x minus 1 equals 3. Use algebra to solve for x. So we'd add 1, divide by negative 1. X equals negative 4. Now watch, let's go check it. Yep, So let's plug in -4 up here. Take your calculator. We're plugging in -4 plus 1. So what do you get when you calculate that? 125. So it really did truly work out. So you can always check your answers with these. So we just got them in the same base. So you knew it was 125. Little butthead. Okay. So looking at this, aren't they the same base? Same base. So we would say 2x minus 1 equals 4, solving for x, would be x equals, you'd add 1, 5, divided by 2, 5 halves, right? Okay, let's do this one. Since they're base E, we can set x squared plus 6 equal to 5x. It's a quadratic. How do we solve quadratics? No, last choice is quadratic formula. To be able to solve a quadratic, we have to first get it set equal to 0. Subtract 5x and put it in standard form. X squared minus 5x plus 6 equals 0. I always solve by factoring if possible. So what multiplies to be 6 adds up to be -5. 3 times 2, negative. This factors to be x minus 3, x minus 2. Thus, x equals 3, x equals 2, correct? -6 and 1, good question. Won't work because that would multiply to be -6. I'm glad you asked. Okay, so we have those solutions, and guess what? I was like, okay, I'm going to go check those. And I went and plugged them back in, and we get e to the 3 squared plus 6, that's 9 plus 6, which is 15, equals e to the 3 times 5 is 15. So we know that one works. You see how to check your answers, everybody? Yeah. Because like anytime we want to check an answer, we take our answers and plug them into the original problem. Which part?
So there's 2 answers?
Yeah.
Wait, so how do you check it?
How do we check any solution? We take it and plug it into the original problem. So 3 squared is 9 plus 6 is 15. 5 times 3 is 15. Is that a true statement?
Yeah.
So we keep the solution, yes? Yeah. So let's plug in 2.
Oh, it works.
4 plus 6 is 10, correct?
Yeah.
Plug in 2. Here we get e to the 10. So they both really did work. So I know I did them right without even having to check anything else. Okay, there's the homework problems.
What's the movie now?
Perfect, 45. You have a few minutes to write that down.